What are we going to pass it with? Hydrogen. That's exactly right. Okay. So we are going to get two hydrogens that come across, and then this electron is going to be passed down these series of cytochromes or proteins that are embedded into the mitochondrial membrane until we get to this area right here. Okay. And that electron is then going to be passed back through to the matrix as hydrogen, and it's going to bind with oxygen to produce water. Okay? So we've taken it, we've allowed these electrons, which is a negative charge, to be passed down. We get to the final stage, we don't want that negative charge just rotating around because it may affect something. We're going to have it bind to oxygen. Okay? So electron transport chain, boom, 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 okay, is going to pass that electron down through the chain. Okay? But what else is happening as we go each step? So here, the first phase, first protein, we get an electron goes, what happens? We get hydrogens that are pumped across, okay? We pass it on to this, what's CoQ? You guys take supplements? Coenzyme Q, right? So the theory is if you take supplements, coenzyme Q, it's going to embed in the mitochondrial membrane, going to help you with aerobic metabolism, okay? Does that happen? I don't know. Good thought, I guess. Okay? So, electron is transported down to the next step, hydrogens come across. Next step, hydrogens come across. These hydrogens are now going to be the important part of us producing ATP. So now we have this gradient of hydrogens on the outer mitochondrial compartment, and they're going to go to this last step, which is ATP synthase, which is what? It's a membrane-bound enzyme. ATP synthase, what's it going to do? It's going to synthesize ATP, right? Okay? And by doing that, what it's going to do is it's going to pump these hydrogens. Oh, that just changed. Ooh, look at that. These hydrogens now are going to be pumped across, back across against that concentration gradient through the enzyme, ATP synthase, and ADP plus 3PI gives us 3 ATP as those hydrogens go across there, okay? So this isn't very good, in my opinion. This is the electron transport chain. It has all the components of the electron transport chain, but it doesn't do it justice. So that's why I put this link in. And so we just found out that if you click on that link, or if you type it in and hit enter, it doesn't go to the page. Is that correct?
Yes.
So go type it in into Google and search for it, and then click it, and it'll give you that, okay? This will come up, and it'll be a flash player that you can play, okay? So what I want to do is watch this. I'm hoping that, can I make that bigger? Make the window bigger, but it doesn't make the flash player bigger. Okay, so let's start this and see what happens. Okay, so here we go. Intermembrane space, intermembrane mitochondrial matrix. Okay, I'm going to continue. Zooming down in. Look familiar? Okay. Our membrane-bound proteins. What's this one right here at the end? It's the ATP synthase, right? Okay. You see our NADHs, our FADHs. Okay. See what happens now. Okay? Did you see what happened? NADH, electron was passed. Each time the electron was passed, how many hydrogens came across? Okay, electron was passed, made water here in the end. Okay, so we had for NADH, how many hydrogens went? 3, right? Okay. Now let's go look at FADH. What's different about FADH? Let's look at NADH. How many hydrogens came across?
3.
3. Okay. Let's look at FADH. Where does FADH start? skips that first membrane bound protein, correct? Okay. And how many hydrogens came across?
2.
2. Okay. So from our old school math, which is different than our old school, so let's put FADH, we had, and our hydrogens went across with 3. How many hydrogens went across? 2, right? Okay. So now let's look at the final step here, see what happens. Okay. So how many hydrogens came across?
3.
3. And how many molecules of ATP did we get?
3.
3. So okay. So if there was 2 hydrogens coming across from FADH, how many ATP would it produce? It would only do 2, right? Okay. And when we first started, I told you there was old calculations for how many ATP you got for NADH and new calculations, right? What were they? So that's the new ones. What were the older ones?
2.
These right here, okay? But it didn't account for getting the NADHs to the mitochondrial membrane, okay? So that's where that came from. The 3 and the 2 is based upon the number of hydrogens that go across and then are pumped through the ATP synthase. So now we know that you get 3 ATP, but it takes a half an ATP to get NADH and FADH here, okay? So the calculations are, now we know 2.5 and 1.5 ATP per NADH molecule in the electron transport chain. Okay? So this, I think, is a better representation. You actually, if you look at this, and now, wow. Look at this. With the information that you had from the video, this makes a lot more sense now, doesn't it? As your NADH comes in, it passes that electron down, binds with oxygen to give water, okay? Hydrogens are pumped across, and then we pump those hydrogens back across to get ATP, okay? So the question is do the hydrogens match here? Why not? In the diagram that I showed you, only 1 hydrogen went across, right? But we still get 3 AP. 3 here, why? There's got to be some hydrogens for that oxygen to bind to, okay, with that electron. So some of those hydrogens are going to come across and be binding for that water. We only get 3 ATP per NADH, 2 ATP for FADH, okay? So when we were doing our accounting, we had Austin go up to the board and do quite a bit of accounting, did we not? And it looked something like this, didn't it?
Yes.
So what is the green box over here?
That is
It's glycolysis, right? Taking a glucose molecule, breaking it down to 2 pyruvate molecules, okay? We get a net yield of 4 ATP, or a total production. The net is 2 because we use 2 in the energy investment phase, right? And we had 2 NADHs that then are going to go to this box. What's this box? That's the electron transport chain in the mitochondria. So NADHs from glycolysis go there. We get 2.5 ATP per NADH 5. Right? So now we have this phase right here. What's this?
That's stage 1.
Stage 1, right? Pyruvate to acetyl-CoA. Okay? Stage 1 of oxidative phosphorylation. We get 2 NADH there. Why? Because we started with 2 pyruvates and then with 2 acetyl-CoAs. Okay? So we get 2 NADHs that then go here to the electron transport chain, 5 ATP there, okay? Then we get into the Krebs cycle. Krebs cycle, we have 2 acetyl-CoA that are going to go around. One is going to go around, the other one's going to go around. And for each cycle, for 1 acetyl-CoA, how much will you get? You get 3 NADH, one FADH, and then one what? GTP that then's converted to what? ATP. Correct. Okay? So if that goes around twice, double it, 6, 2, and 2. So do we get those numbers? Yep. Take the NADH, 6 times 2.5 equals 15. 2 FADHs times 1.5 equals 3. And then those 2 GTPs that are converted to ATP gives you 2. If you now take the total from one glucose molecule that goes through aerobic glycolysis through glycolysis, stage 1, stage 2, and stage 3 of oxidative phosphorylation, you should get a total of 32 ATP. Okay? Our accounting should come up to that. Is that what we got on class Monday? Austin was 32. I think we did, didn't we? We did pretty good on the math. Okay? So, question is now, what would the total be with glycogen?
33.
33. Why?
Because it doesn't have to go through that initial investment.
Because this initial investment phase would now go to 1, and this one would come over and be 3. Total would be 33. Correct?
Yes.
Everybody buy that accounting? So the next question is what, let's erase this again. If it didn't cost us half an ATP to get NADH and half an ATP to get FADH into the mitochondria, what would the total yield be?
33 and 34, right? No.
So instead of taking all these, you take this one by 3, this one would be by 3, this one would be by 3, what would this one be by? Be 2, right?
Yep.
And so what would our numbers be now? So we have 2 NADH coming times 3, this would be 6, this would be 6, what would this one be? 18, what's this one going to be? 4, add that up 1. Does everybody get that?
Mm-hmm.
Some textbooks may tell you that it's 38 ATPs produced for a molecule of glucose. So now you know what that difference is, okay? They're using this nomenclature where they're accounting for FADH as 2 ATP and NADH as 3 ATP. Forget all of that. We are 32, okay? Because we know that it takes energy to get those electron transport carriers into the mitochondria. So now you know everything you need to know about metabolism, correct?
For the test, maybe.
No, you know everything now, right? Where do fats come into this show? So if we go back to a slide that I showed you earlier, where do fatty acids come into this? Right here. Okay, and then they're broken down to acetyl-CoA. Go through the Krebs cycle, go through the electron transport chain. So we'll produce as each acetyl-CoA goes through, we'll produce 3 NADH, 1 FADH, 1 GTP that's converted to ATP. What's the difference between this and going through the Krebs cycle and fatty acids? Just a lot more acetyl-CoA in the triglycerides, right? So more energy because we can send more acetyl-CoAs through them, okay? But guess what? Krebs cycle, electron transport chain, great news, they stay the same whether it's fatty acids or amino acids, okay? You're just breaking down those to acetyl-CoA so that you can get them into stage 2 and stage 3 of oxidative phosphorylation. So if you know it for carbohydrates, guess what? You know it for fats. You just have to keep track of more things because now there's more acetyl-CoA, okay? And on that tune, are you ready? No. So, accounting, keeping track of it. Great news is if you like it in a table form, here it is in table form, okay? Gives you the equivalents for NADH and FADH. However you want to look at it, table form or figure form, guess what? Number's the same. 32, 32. Just means if you're a visual learner and you like this one better, you take this one. No, you got a question?
Yeah, I'm just getting conflicted on the electron transport chain between the picture and the video.
Okay, what's the conflict?
So how come we're showing that 2 hydrogens are being transported across in the very first step?
So they don't show those 2 hydrogens here in that video because they only go back through here. They end up being, some of those hydrogens are used for that water.
Okay.
So the only thing that you need to know is that when one hydrogen goes through, you get an ATP. So that's what I want. So I don't really like this one as much, but it's the standard one that they have on there. And there's a lot more going on than what you see here too. So if we were to look at this biochemically, a lot more going on. So what I want you guys to focus on is NADH. The reason it gives you 3 ATP is because it starts earlier in the chain at this first protein complex, and so that it now has the electrons being passed through 3 different proteins, gives you 3 hydrogens that go back across, okay? And then FADH comes in later at coenzyme Q, so only 2 go across, and then gives you the 2 ATP, okay?
So we would get 5 ATP total or no?
So,
Or your 2 is going to make water.
so each one of these is, so you would get this, and they go down here to make water. Yeah, so it has to balance out that electron charge, right? So that's what those other hydrogens are used as well. Okay.
That's why in the video 5 went across and you got.
Yeah, that's exactly right. So in the video, it only shows the hydrogens going across that are then converted to ATP. Does that make sense? Does that clarify your question? I think that's more
Yeah,
direct.
so I was just confused because we had 6 and then the other one was 5.
Yeah, so good news is you will not have to draw this. Okay? You just have to understand how it works and how many ATP are in there. Okay? I would never make you draw that. In an advanced class, we'd be drawing it and we'd be talking about all the stuff that you want to talk about. But this is, in my opinion, it's just confusing enough as it is. If we add more details to it, it just ends up going, you're like, it doesn't make sense. All we want to know is we're making ATP from aerobic breakdown of a carbohydrate, okay? We can talk about the other stuff when we realize we know what's going on. We'll talk about the advanced stuff later on, okay? Talk about carnitine and carnitine transferase and all those things and get those things in there, yeah. That's a whole other, yeah, it's not really. I took a whole 2 semesters of biochemistry, just 9 hours of biochemistry every week. It's great. I'm not saying it's not important, Carmen. You don't have to give me the poo look back there about biochemistry. It's important. It's just not very exciting, okay? Questions? That's a good question, though. So, all right, let me sit down. Go back to the JIT Scholar board. How's that work? Everybody comfortable with metabolism?
Like maybe half of it.
Maybe half of it. Good news is you have about how many days? 5 days to study. Good 2 weekends. Austin doesn't have anything to do, he said. Didn't know he said earlier. Pretty light day today. Maybe you can get that in there. Okay.
Sleep for 6
Yeah.
hours.
Nothing going on. Let me start by saying I don't care what's going on in the rest of your life, Austin. So you don't do well on the test, don't come to me and go, well, I had this, I did that. Well, yeah. Just let you know. It doesn't work for me. We're here as students. Winnie's already had that conversation with Captain Roly-Poly down the thing. Does he know what's going on? You can sit in here and answer questions about metabolism, okay? So, fats and proteins. Not going to talk much about proteins, obviously, but we know where it goes into. It's broken down into amino acids, and we're going to convert it to acetyl-CoA and have it go through, okay? we're now going to talk about fats and specifically how we get fats to that point in glycolysis, okay? So one of the things is we're going to be talking about a process called beta oxidation, which is taking fatty acids and converting it into acetyl-CoA so that we can run it through the Krebs cycle, okay? So let's look at this right now. Oxidation of fat. So this is a chemical formula for a triglyceride, okay? Why do they call it a triglyceride? Each one of these is what? Fatty acid bound to a glycerol backbone, okay? And what we are going to do is we are going to break off those fatty acids, convert them to acetyl-CoA so that we can use it to convert it to ATP, okay? We'll also be able to use the glycerol backbone. It doesn't give us much, but it does give us a little bit of ATP, so we're not just wasting the glycerol backbone with us, okay? We also know that this is the majority of our energy, okay? We can store a lot more of it. How many kcals of glucose or glycogen can we store? About 2,500, okay? So if we use fat cells and muscle cells, we obviously increase that by a huge margin in regards to the number of kcals that we can use with fats, okay? So the problem with that is what? It's on this slide. It's stored in fat cells. So do fat cells undergo muscle contraction? No, they don't. So we've got to get triglycerides, the storage form of fatty acids, from adipocytes in areas of the body to muscle cells. Now, good news is we do have a little bit of stored triglycerides in muscle cells. Again, very small amount, 2,000 to 3,000 kcals, just enough probably to prime the system if we're going to use free fatty acids as a predominant energy source, okay? So that we can then start the system going, and then once the delivery comes from the adipocytes, we can do that. So the question is then, how do we get fat into skeletal muscle so that we can use it for energy? So one of the things we're going to do is we're going to break it down. Lipolysis carried out by lipases, which are enzymes. Okay, we break that down into the 1-glycerol and 3 fatty acids. So now we've broken it down. We have access to the free fatty acids, but how do they get there? Okay, everybody got that before I go on?
No,
We
it's
still-
okay.
We can still break them down, but we still have to get them to the muscle cell, okay? So that rate of free fatty acid is going to depend on a concentration gradient, okay? There's less fatty acids in the muscle, and then we haven't got to how we're getting it there, then it'll come across. How do you think it gets there?
The energy or
Not the energy, the free fatty acids. How would this still how the cholesterol maybe, but how does it get there?
it's broken down first, drop the bloodstream.
Ah, there you said the word. What was the word you just said that was the most important thing right there?
Bloodstream.
Bloodstream. It's going to be carried in the blood to the skeletal muscle. Okay? So everybody ready now? So here we have a diagram on the right, shows our triglycerides stored in adipose tissue. Okay? We have hormone-sensitive lipase, which is a lipase that breaks down triglycerides into fatty acids and that glycerol backbone. And just like Austin told us, fatty acids are going to bind with albumin in the blood, okay, so that we can transport it to skeletal muscle. So why do we have to bind it to albumin?
Transport protein.
Say it again.
Transport protein.
The transport protein, but why would we have to do that in the blood? That's exactly right. So fats aren't compatible with solute, right? So it's going to be a problem. You have to bind it to albumin so that we can get it to where we want it to go, because it's not going to dissolve in the plasma. You have to bind it to a transport protein, which is albumin. Then albumin will release it, and that concentration gradient that we're talking about is this right here. Will come across if there's low free fatty acids in the muscle and the concentration is higher in the blood, fats will go into the muscle, okay? And so then what happens? This is now where we start what we just talked about before. We are now going to take fatty acids, convert them to acetyl-CoA, okay? Go through the citric acid cycle, the electron transport chain, and give us ATP. Everything that we just talked about. Now, here we also said that we could use the glycerol backbone. So that glycerol backbone is also going to be transported to skeletal muscle, okay? And it can be converted to glucose and then, again, go through stages of oxidative phosphorylation to produce ATP, okay? We'll talk about those numbers. So, beta oxidation is converting fatty acids to acetyl-CoA. So it's this step right here where we're converting fatty acids to acetyl-CoA so that we can get them through the electron transport chain, Krebs cycle, and the electron transport chain, okay? And we know that it's going to enter the Krebs cycle. We're going to get how many NADH per molecule of acetyl-CoA? One acetyl-CoA will give you how many NADH in the Krebs cycle? Three. How many FADH? One. How many GTPs? One. Exactly. Okay. The accounting's the same because it's a one acetyl-CoA. We're just going to have more acetyl-CoA. Okay. We're going to talk about this in detail as we chop these two carbon fragments off, forming acetyl-CoA. This is where we get the energy, okay? One of the other things that we're going to need to know about beta oxidation is this point right here. We also have to invest in it, okay? So there's 2 ATP that are required up front as we break down a free fatty acid. And it requires oxygen because of the number of carbons based that each breaking off of that is going to require some oxygen. So there's more oxygen used due to the higher carbon content compared to glucose. I think the next slide. Not the next slide.
Is it possible for someone to have more fatty acids in their muscles, which would not allow as much to go in?
So could you store more fatty acid in your muscle so that gradient isn't there?
Yeah.
Potentially. There's also things that go on with regards to inherent errors in metabolism. So let's say you can't get fatty acids to the mitochondria or things like that. So there are people that have mitochondrial disorders that affects their ability to exercise. So a number of things. If you think about all of the cascades that we just talked about, glucose going through glycolysis, through stage 1, through stage 2, through to stage 3, the electron transport chain. How many steps are we talking about to convert one molecule of glucose to get 32 ATP? A lot. So now let's think about one of those steps, one enzyme doesn't work well. Okay? Is that going to have an effect on our ability to use energy? So let's talk about it in glycolysis. So if glycolysis, if you had an enzyme that was bad, would you still be okay maybe?
Depends if it was in PFK.
Yeah, but even if I think you had an inherent error in glycolysis, the good news is based upon this slide right here. Has everybody got this one? Don't you got it?
Just about.
Okay.
Getting started would be hard, but eventually get into a aerobic.
That's exactly right. So you're thinking exactly correct, Austin, in that if you look here,
is if we had something that was wrong with glycolysis, maybe we're now eliminating this, okay? But we still could potentially, if everything is working on the fatty acid side or the amino acid side, we could get it converted to acetyl-CoA and go through the Krebs cycle, and then our NADHs, FADHs are gonna go through the electron transport chain. Now, if we get it into the Krebs cycle, let's say one of the enzymes doesn't work in the Krebs cycle, now we're running into a problem, okay? Because we're gonna affect the ability to break down foodstuffs and get maybe, let's increase that one. Maybe get some that are functioning normal-wise. But the bad news about this is this is a cycle. So if you affect any enzyme in here, oxaloacetate is needed for the Krebs cycle to run, okay? The reason it's a cycle is you're regenerating that oxaloacetate every time to start it with another acetyl-CoA. If you stop it somewhere, you're now not getting oxaloacetate to start the Krebs cycle. That's going to be problematic, okay? Now, this is all going to the mitochondria. What if we have transport proteins that aren't allowing us into the mitochondria? And that's what some of these people that have mitochondrial disorders have, is they can't get things into the mitochondria to do aerobic metabolism. So their ability to exercise is completely diminished because they are unable to do oxidative phosphorylation. So a lot of things go wrong. You know. Same with your comment too, is what if you have something with regards to high storage of fat in your skeletal muscle, and it affects the concentration gradient. Fats aren't going to go into the muscle as well, so are you going to be able to use them as an energy source? Okay? And I'm sure there's probably some disorder.
Doesn't you know the disorder that has increased fat in the muscle?
I can't think of one off the top of my head.
Diabetes?
Decrease, but not increase.
So what's going to happen with diabetes?
Like type 2 diabetes maybe?
So type 2 diabetes affects what?
Like the insulin can't make it to the cell. It's being blocked out.
So
by
let's
fat acid.
we'll talk about this in detail when we talk about hormones. But what does insulin do?
It shows glucose to the cell.
Allows glucose to enter into cells. So what does type 2 diabetes do?
I get the type 2, the inherited one.
No, type 2 is the other.
Type 1 is inherited.
Decreases your insulin
You don't let it
sensitivity.
It decreases insulin sensitivity. So your insulin that you're producing isn't as responsive in cells,
Mhm.
okay? Because of your metabolism is out of whack, and you usually have higher insulin concentrations. And so what happens is you either have decreased receptor sensitivity or downregulation of receptors, so insulin can't bind, allowing glucose to enter the cells.